In papers 52 through 54, we analyzed the Ulam spectrum at the B2 spray point, focusing specifically on the parameter value where epsilon equals 0.70. This split-screen diagram visualizes the two distinct states we documented in that spectrum. On the left, the leading eigenvector, V1, is locked as a perfect single-cell delta spike. On the right, the subdominant deep spectrum, tiers 2 through 10, takes the form of highly oscillatory dense wave packets that we refer to as dark matter. There is a standard mathematical assumption regarding this type of boundary grid geometry. The established folklore holds that at massive grid resolutions, the exact subcell placement of the partition walls becomes irrelevant. The scale of our models clarify why this assumption exists. At a resolution of 16,384 cells, a single cell width, or delta x, is roughly 0.000366. When boundary cells are that microscopic, sliding the overall grid alignment by a subcell fraction should theoretically have zero impact on the resulting spectral geometry. Paper 55 tests this premise directly. We need to determine if that frozen V1 spike is a true physical singularity of the map, or if it is merely a numerical artifact resonating with static boundary walls. This diagram shows a 1D number line divided into equal cells. To conduct our test, we open the partition axis. We freeze the map, the kernel, and the grid size and introduce a single new parameter, a grid phase shift, delta. We uniformly shift the entire matrix of vertical cell walls to the right by a fraction of a cell's width. We execute this delta shift at exactly 5 equally spaced subcell phases, 0, 0.2, 0.4, 0.6, and 0.8 times delta x. The delta 0 state is left untouched to serve as the absolute paper 54 baseline control column. Opening the partition axis applies a definitive stress test. It will reveal whether the boundary Ulam grid is capturing genuine map physics, or if it manufactures artificial geometry based on where we draw the cell walls. We begin by focusing exclusively on the leading eigenvector, V1, at our highest executed resolution of 16,384 cells. At the delta 0 baseline, this state is perfectly rigid. It is locked precisely at cell index 3101, with a cumulative mass width, or K90, of exactly 1. We initiate the experiment by systematically shifting the grid phase delta through the 4 fractional subcell steps. Because this state is concentrated into a single microscopic cell, altering the partition alignment over it might be expected to shatter the invariant density proxy or violently disperse its mass. That does not happen. The spike remains localized within the same microscopic neighborhood, showing no evidence of vanishing or jumping to a distant part of the interval as the walls slide. We see the dominant cell index drift slightly within a narrow band, moving between index 3101 and 3069, but it stays anchored near its original position relative to the 16,000 cell grid. Across all 5 phase shifts, the delta spike never broadens, and its mass never bleeds into adjacent cells. The final recorded metrics are absolute. For all pairs of grid size and phase shift, the K90 width remains locked at 1, and the top 1% mass holds at exactly 1.0000000000. The leading singularity is conclusively grid robust. The V1 delta spike is a physical reality of the map, and not a fragile artifact dependent on Ulam cell boundaries. We then pivot our analytical focus from that robust leading state to the subdominant deep tiers, examining V2 through V10. Recall that these deep tiers have a highly specific geometry. They form ultra-high-frequency, spike-dominated wave packets. Unlike the leading spike, which ignored the subcell shifts entirely, sliding the delta parameter causes these deep wave packets to react violently. This dashboard shows the mechanism in action. The deep tiers fall into a grid phase trap. As the partition walls slide, the wave packets experience spatial aliasing, expanding and contracting in width based strictly on the grid's movement. The most extreme limit of this behavior occurs in Tier 9, precisely at the phase shift of 0.8 times delta x. At that exact alignment, the wave packet undergoes its maximum structural expansion. The cumulative mass width, K90 for V9, scales up from its baseline to 11 full cells. To maintain exact proportions, an 11-cell width represents clear aliasing, but it remains microscopically thin relative to the full 16,384-cell grid. We see corroborating evidence at the coarser grid resolution of 8,192 cells. Here, the grid phase shifts also force the deep tiers to broaden, reaching a maximum K90 width of 7. Despite this physical broadening, the internal mass concentration stays extreme. The wave packets retain top 1% mass values virtually locked at 1.0, dipping no lower than 0.99999. While the leading state remains untouched, the geometry of these deep-tier wave packets is dictated by the alignment of the grid, a numerical trap where discretization masquerades as map physics. Pulling back from the subcell level allows us to evaluate the complete Ulam spectral geometry at the B2 spray point in totality. This data table shows the bifurcated reality of this numerical method, separating the narrow ranges of observed cumulative mass widths for the first eigenvector against the wider alias ranges for tiers 2 through 10. As the top row indicates, the Lorentzian leading state is completely immune to grid phase variation. Its structural physical validity is intact. The deep tier rows map out the failure. The dark matter wave packets are demonstrably aliased by the exact placement of the cell walls, validating the grid phase trap. The eigenvalue mechanics share this linkage. The deep tier eigenvalues fluctuate with the delta parameter because the Ulam matrix is resonating with its own shifting partition, rather than detecting new dynamics within the map. To properly utilize these findings, we must strictly enforce 3 operational guardrails. First, all conclusions drawn here are rigorously scoped to the finite grid. Second, these aliasing results cannot be extrapolated to continuum operators, nor do they support asymptotic phase claims. Third, the scope is restricted solely to the specific executed grid phase shifts on grids of exactly 8,192 and 16,384 cells. Within those bounds, the baseline infrastructure remains reliable. The certified bounded variation spectral gap we established in Paper 37 remains untouched and mathematically sound. Paper 55 confirms that at the B2 boundary, the Ulam matrix operates in 2 decoupled realities. A highly robust invariant density proxy sits atop a deep spectrum whose exact geometry is trapped by the microscope observing it.